We will now look at some alternative forms of expressing equilibrium conditions. And first we're going to look at an isolated system. Let's suppose that we have an isolated system A star that is described by a macroscopic parameter y. So we're considering A star an isolated system, so it doesn't exchange heat or there is no work being done on the system by the environment. It's an isolated system that is described by a macroscopic parameter y. And we would like to know at equilibrium what is the probability of this parameter y having a certain value. So what can this y be? You can envision that we have this isolated system A star consisting of two subsystems A and A prime that are in thermal contact. So here is the thermal contact between A and A prime. So this is system A, this is system A prime, and what I call y, the macroscopic parameter of system A star. So A plus A prime is A star, which is isolated, and I have the macroscopic parameter y is E, which is energy of system A, the total energy. Or I can give another example. Let's think about the same combination of systems A and A prime, but this time I'm going to have a movable piston in between the two systems at the boundary. So there will be a movable piston here. So that there can be energy transfer in the form of work. So between systems A and A prime. This one is a movable, a free piston, let's say. And now what I call y, if I define my coordinate system like this, y is the position of the piston. So there will be a corresponding number of accessible states to system A star. So omega star, the number of accessible states to the isolated system A star, is a function of this macroscopic parameter y. And its corresponding entropy, total entropy S star, is k ln omega star. So it is also a function of this macroscopic parameter y. And you can divide the y parameter into fixed size small intervals. So if y is divided into fixed size intervals, delta y. So delta y is chosen small enough that the number of accessible states omega star does not change if y goes from y value to y plus delta y value. So I call Py the probability of y being in the range y to y plus delta y. And that has a fixed, as I said, there's the change in the number of accessible states when y changes from y to y plus delta y is negligible. So that's how we have chosen delta y. And at equilibrium, we're going to have the probability of having a value of y in the range y to y plus delta y proportional to the number of accessible states to the system A star when y has this value in this range. And as you can see from this equation, that this is basically exponential total entropy as a function of y divided by k. So that basically describes the probability of y having a value, a certain value, within a small uncertainty delta y. Now we find that the entropy is going to have a sharp maximum at a certain value of y, that is y tilde. So at equilibrium we will, with highest, the most probable y value that we will measure will be equal to y tilde, where the entropy will be maximized. Now we can see this if we have a reference macro state. So for example, if y value equals to y0 at some standard macro state, which is our reference, then we can calculate the probabilities in reference to this macro state. So probability of y having a value y to y plus delta y divided by the probability of y having a value y0 plus y0 to y0 plus delta y will be the ratio of the exponentials s star of y exponential s star of y divided by k and exponential s star y0 divided by k. So you can see that the probability of y having a value in the range y to y plus delta y will be equal to a standard macro state probability P0 exponential change in entropy delta S star divided by K. You can see that the change in the entropy delta S star is S star when y is equal to y plus delta y minus S star when y is equal to y0 plus delta y, or y0 to y0 plus delta y range. And we define P0, the probability of our reference macro state where y has a value y0 to y0 plus delta y. So you can see here that the probability of having a certain y value in reference to this macro state where we have y value equals to y0 is exponentially growing with the change in the entropy. So what can we learn from this? So we can say that the most probable value of y corresponds to the highest entropy. Why? Because we need to have delta S star maximized, so it's exponentially growing with increasing entropy. So the most probable value will have the highest possible entropy of the system A star. So the total entropy must be maximized. So the total entropy will be maximum at y equals y tilde, the most probable value. So we can state this by saying the equilibrium situation of an isolated system is characterized by values of its parameters such that the entropy of the isolated system is a maximum. So this basically describes for us the equilibrium macrostate of an isolated system. Now, if we have a value that is other than the most probable value, then the system will approach to equilibrium, and in doing so, it's going to be increasing its entropy. So since we have for the total entropy a star at value y equals y tilde, so this has a sharp maximum at y equals y tilde. If we prepare this system at a value that is not the most probable value for this parameter, so we prepare the system at a macro state with a corresponding value of y that is not equal to its most probable value, then it will approach the equilibrium, and that will be corresponding to an increase in the entropy. So y is going to approach y tilde, and at the same time we will see that the change in the entropy will be greater or equal to 0 for approach to equilibrium. Now there is an interesting situation if we have the entropy dependence on y, not like this with a single maximum at y equals y tilde. We can have a situation where the entropy changing as a function of the parameter y, s star as a function of y, shows two maxima like this. And there is a local maximum. So this one is a local maximum, and this one is a global maximum. And basically the question I would like to ask is, what happens if this system is prepared at macro state A with its corresponding y value, ya tilde? The answer is, because the journey from macro state A to macro state B involves a decrease in the entropy of the system, so that means we will go through a macro state that is very unlikely. The system will remain in the metastable equilibrium at macro state A. So that is an interesting situation. So we find that if the entropy as a function of this macroscopic parameter y has a local maximum at macro state A and a global maximum at macrostate B, if we prepare the system with the macroscopic parameter y close to ya tilde, the system may remain in the metastable equilibrium. Metastable equilibrium point is y is equal to ya tilde. This is going to happen because the most probable state to reach the most probable state which corresponds to y is equal to yb tilde, it has to pass through a y value which is between ya tilde and yb tilde, which has very improbable situations. You can see here that the entropy on the journey from A to B is going to be decreasing, and this decreasing entropy is basically making the state here, especially this state here, this state, let's call it C, is very unlikely. It's an unlikely state because it corresponds to a decrease, a substantial decrease in the entropy. So we can give an example for this situation. An example you can think of is supercooling. What is supercooling? Well, if you have a very pure water, cooled gently below 0 degrees Celsius, can remain liquid at a metastable equilibrium easily down to temperatures minus 20 degrees Celsius or even less than that. So you need a nucleation site for the the ice crystals to grow. So for example, if we have a grain of dust is dropped, then it will immediately freeze. So this dust will initiate the ice crystal growth. It immediately freezes. Okay, so we're trying to describe the equilibrium conditions for an isolated system, and we have a macroscopic parameter y. For example, this is the energy of system A in the isolated system A star, where A and A prime are in thermal contact, or it has a movable piston in between the two, and we can call this macroscopic parameter y the position of the piston. Now, what is the probability of having a certain value of this macroscopic parameter y? It depends on, according to our equal a priori probabilities postulate, it depends on the number of accessible states as a function of y, and therefore the total entropy. And at equilibrium, the probability of having a certain value of y is proportional to the number of accessible states at that value to the isolated system, which is the exponential factor S star divided by K Boltzmann constant. And you can see that if you have a standard macro state y, which has a y value y0, the probability of having this value of y is p0 multiplied by exponential change in entropy divided by k. So the most probable value of y corresponds to the highest possible increase in entropy, and so that will be given by, so the equilibrium situation will be characterized by a maximum in the entropy. You can see here the most probable value of y will occur at this maximum, which is the equilibrium macro state. So we will see if you have two maxima in entropy as a function of y, we can have a local maximum and a global maximum corresponding to two macro states A and B. If the system is prepared at its close to its local maximum A, then it may remain there at metastable equilibrium because it takes a very unlikely macro state to reach from A to the global maximum B. And a good example of this is supercooling. If you have very pure water cooled gently below 0 degrees Celsius, it may remain liquid down to minus 20 C, even below. But if you just have a nucleation site created, for example, if you have a grain of dust that is dropped into this, the ice crystal growth will be initiated and it will immediately freeze. Or if you bang it, so you have a certain arrangement of molecules inside this liquid, it may immediately freeze. So there is also a video I would recommend you to see, which experimentally demonstrates how the supercooling process works for a bottle of pure water.